Okay, we're in the home stretch. So in page 1 of the math lab for the Trig Identities hexagon, we learned how to create this hexagon and fill it in to remember trig identities. Then we used it to find the 12 quotient identities, the 6 reciprocal identities. Then we came to page 2 and we looked at the 9 product identities with the hexagon, the 6 cofunction identities. Then in our last video, we derived the Pythagorean identities and then learned on the identity hexagon how to come up with those Pythagorean identities really quickly. So now on our last page, we're going to look at even and odd identities. And that will wrap up the basic identities. There are lots more trig identities that we'll look at as the weeks go by, but this will be enough to get us started with basic trig equations. So for even odd identities, first we need to look at their graphs and recall that functions are considered even if their graphs have y-axis symmetry, odd if the graphs have rotational symmetry. So if we look at the graph for the sine of x, remember it passes through 0, 0, and then also has zeros at pi and 2 pi. Then at pi over 2, it hits its maximum at 1. 3 pi over 2, it's at the minimum of -1. Those are our quadrantal angles. And then we can go ahead and fill in that sine curve. Makes a beautiful wave. Right, that would be the positive side. And then if we follow that pattern for our negative angles, okay, there we go, that's our sine. Okay, and this sine curve shows that it has rotational symmetry about the origin. For example, if I were to reflect it in the x and then the y-axis, right, we would get back the same picture that we had. So since this is an odd function, and we remember that for odd functions, f of negative x is the same or equivalent to negative f of x, the opposite of the function. That means that the sine of negative x would be equal to negative sine of x. Right? And that is our first identity, and that's an odd identity. Okay, then the graph, parent graph for the cosine function. Cosine at 0 has a point up here at 1, and then its pi over 2 is a 0. Then at pi we go down to -1, 3 pi over 2 back at a real 0, and then 2 pi we come back to +1. So if I follow that pattern backwards for the negative angles and then go ahead and put in that curvy wave, right, that would be our graph of cosine. And remember, the graph of cosine is a phase shift because those are cofunctions of pi over 2. So same exact graph, just phase shifted over pi over 2 units for the cofunction. So when we look at this graph, it is definitely not an odd. It doesn't have rotational symmetry about the origin, but it does have that y-axis symmetry that tells us that it is an even function. And here's our rule for even functions. F of negative x is equal to f of x. Okay, so that means the cosine is even, and the cosine of negative x is equivalent to the cosine of x, and that's our second identity. Okay, then the tangent graph is, tangent is undefined at pi over 2. It's undefined at 3 pi over 2, and then negative pi over 2, and negative 3 pi over 2. So those are all vertical asymptotes because tangent is undefined at those places. Tangent is equal to 0. There's real zeros at 0, 0, at pi, at 2 pi. And then we can follow that pattern back for the negative angles. And then we can go ahead and fill in our values in between. And this would be the parent graph of tangent. Okay, so looking at that graph, we can see that tangent has origin symmetry, which makes that an odd function. And so using our odd rule that f of negative x equals negative f of x, the tangent of negative x is equal to negative tangent of x. Okay. Then cosecant. So remember the cosecant graph, the easiest way to find that one is to just roughly sketch in our sine graph and then reflect everything to get those reciprocals. So if I just real lightly pencil in the graph for the sine of x, then I know that all of these maximums for sine and minimums for sine, right, they're going to become extrema for cosecant. And then in between these zeros, when I take a 0 and I take its reciprocal, I get undefined. So those zeros for sine become vertical asymptotes for cosecant. And so we'll put those fences in, and then we just flip this curve, and there is our parent graph for the cosecant of x. And then we can go back in and erase the skeleton that we put in there for sine, and voila. So looking at this graph, we can see that there is rotational symmetry about the origin, which makes the cosecant function an odd function. So the cosecant of negative x is equal to negative cosecant of x. Okay, then the secant function we would graph with the skeleton of cosine. So we'll go ahead and pencil in that cosine skeleton, and then our extrema for cosine will be the extrema for secant, and all the zeros become asymptotes. So there's our fences, and then we can flip over those curves, and there's our secant parent graph. Go ahead and erase the skeleton for cosine from there, since we just use that as a guide. Okay, so we can see in the secant graph that same y-axis symmetry that we had for cosine, which makes that an even function. So the secant of negative x is equal to the secant of x. Okay, then our last one is going to be the cotangent. Everywhere that tangent has zeros, those will become vertical asymptotes for cotangent. And everywhere that cotangent or that tangent had asymptotes, those will become zeros for cotangent. And remember, cotangent is a decreasing function. Tangent was increasing. So cotangent is going to be going downhill between these asymptotes. And there we go. So cotangent also has that rotational symmetry about the origin. So that's going to make it an odd function. And therefore, cotangent of negative x is equal to negative cotangent of x. And there we have it. So those are the even odd identities. Now on the trig hexagon, to remember those, and it's really hard to see this, so I'm going to darken up these sides here real quick so they show up a little better. So on our trig hexagon, this, I don't know if you can see it, it might be a little blurry, but this is a reminder of how you can remember which are even and which are odd. So secant, S-E-C-A-N-T, secant, right? See the E there in secant? Secant is the only one of these 6 trig functions with an E, so it's even, right? Along with its reciprocal cosine. So secant is even, because it's got that E there. Cosine, right, no E in there, so that one is also even. these 2. Okay, these other 4 are odd. So if you remember when you're looking at your hexagon, the only one of these that has an E is secant, and so that one and its reciprocal or they are the only 2 that are even. All the rest are odd. Okay. And the evens, they stay positive. So the cosine of a negative angle is equal to the cosine of the positive angle, right? Evens are going to be positive. The odds, those are going to be negative. So the sine of a negative angle is equal to the negative sine of the angle.